Relative relief can be used alone to give the impression of topography or elevation change, or can be used in conjunction with contour lines, spot elevation, things like that, that would combine that relative relief with absolute relief. But they help provide a context. They help illuminate or make it clear how the elevation changes. It can provide a three-dimensional effect. So we're going to look at hypsometric shading, shaded relief, and raised relief, and then we'll go on to finish up talking about digital elevation models and Lidar. So hypsometric tinting or color tinting is a way of grouping elevation ranges and then showing that color as you kind of in a way thinking of a choropleth map, but not always using the same hue, to show high elevation and low elevation. And so it can be added to contour lines, and then so the shading would kind of correlate with different contour intervals. And so it's a nice way to help people decipher and interpret elevation. Another useful tool is shaded relief. And so this map has shading that lets you, it looks as if the sun is coming from a specific angle that helps illuminate the topography. So you can actually see that this is a ridge, not just that there are contour lines close together. So this is shaded relief, which is used in conjunction with the contour elevation, and it also might be a little bit of hypsometric because you've got green in the lower elevations to kind of browns in the upper elevations. Another common way to show relief and elevation is using vertical models or raised relief models. So if you're doing typically a raised relief model has a little bit of vertical exaggeration so that you can actually see the difference or feel the difference. So here's a real common topographic map, and there's probably information here that talks about what the elevation exaggeration would be. Here's a nice kind of grayscale raised shaded relief of the United States. You can see the Appalachian mountain chain, and then you kind of see this big Midwest plateau, the Central Valley in California, and then this whole basin and range in Cascades and Rockies showing up very clearly. This map is using a very detailed elevation data called Lidar, and it makes very amazing topographic or amazing elevation maps that show very detailed contours of the landscape. So this again is being shown as a shaded relief, and I don't think there's any. No, I don't see anything on here as far as absolute elevation, but you can definitely, from the shadowing, see that this is steep, this is higher than this area here. Here's a shaded relief in grayscale. Very elegant looking map. The contours are really easy to see, and yet I get that sense of the change in elevation here, and this really demonstrates that shallow slope or very low slope, the contour lines are very far away. The very steep slope, those contour lines are really close. And this shows that bowing pointing downhill and a little bit more of the points of those contours pointing uphill. Here's another nice kind of color shading of Crater Lake. And then, so not to beat this point too much, but so up until now you've worked with primarily vector data. Your base maps have all been imagery, but most of the layers that you've added have been either a point, a line, or a polygon. We've started working with shape files, and you created points out of a CSV file. You created points and lines and polygons using KML in Google Earth. And so we're going to switch, when we look at elevation, we're going to switch to the raster model for data. We're going to be looking at a digital elevation model. And the raster data, I just want to enhance this just a bit, without pixelating it. So the raster data has one XY coordinate, and that is at the origin of the raster. And then instead of an XY coordinate for every corner, the number of cells is given and the size of the cell is given. So that if you know the cell size and you know the beginning for your latitude and longitude coordinate, then the computer software can draw the rest of the grid. So each of these grid cells has a number in it, and that number could stand for, probably not elevation because the number is pretty small, but you could be looking at a very detailed map of a small area, and there's not much elevation change. But if you put that grid, but let's say this grid is 10 meters by 10 meters. Okay, so each of these covers a 10-meter area, and it's just draped over a landscape. And let's say that the numbers stand for a type of vegetation, so that a 0 might mean open water, a 4 might be grassland, a 9 would be Douglas fir forest. And so each of these 10 meter by 10 meter squares is generalized by the predominant landscape in that area. Now when we go to a digital elevation model, we're able to use those rasters or that data to create a 3D image or representation. And so in a DEM, every grid cell has a value for the elevation of that grid cell. Sometimes it's an average, sometimes it's the elevation of the center of the cell. There are different ways to determine what value you're going to give that cell. When you look at a DEM in ArcGIS or in QGIS, you see squares. Each of those squares is a grid, and they tend to be very hard to distinguish the shading between the grid. But for example, I put a blue square over one of the grids, and using the ID tool, it told me that that cell is 515 feet. It has a value of 515 feet. So what it's telling me is that in that 10 meter by 10 meter square, everything is going to be given that same elevation. And down this lower southeast corner, that grid cell is 535 feet. So once I have a DEM, there's a lot of things that I can derive or I can create based on that absolute data. I can create a hillshade that will look better than that, I hope, but somewhat like that. I can create a map that tells me what is the slope, whether the slope, percent slope, or the aspect, which direction it's facing, and then that can be used to create general stream flow directions and channels. One of the newer things in elevation is Lidar data, and Lidar stands for light detection and ranging. This is remote sensed imagery from a plane, or they're using drones right now, and so also for just smaller areas. But being able to fly over an area, send out a Lidar beam, and then receive information as the bounce back from that Lidar pulse, telling you how long it took that pulse to reach the Earth's surface. And so what happens with a plane or a satellite, there are over 400,000 pulses of light per second, and the receiver picks up that information, and the time that it takes that pulse to hit the surface and return is used to develop points that show the elevation. And from that they can use a bare earth Lidar, which shows as if there were no trees or buildings, what was the ground look like, or it can show tree canopy and building tops with Lidar. So the very cool thing about Lidar is that it gives you an amazing resolution. So on the right, this is a DEM that has 10-meter grid cell showing Mount St. Helens, and these are spectacular. But on the left, this is a Lidar digital elevation model showing Mount St. Helens, but the cell size is 0.5 meter. And these files are huge. I have a terabyte worth of data from just the Willamette Valley Lidar set.